Welcome back to Zero Dark Emissions. Last time we left off with the installation of the front motor and gearbox, and in this episode we will start the installation of the main battery box. This episode, along with the next several episodes, will be the main part of the EV portion of the build. As discussed previously, we will have a main battery box that will sit within the tunnel, as well as a secondary battery box under the hood that will fit the remaining needed batteries, along with some additional high voltage equipment, which we will cover in a later episode. As mentioned, we will be using 18 Tesla Model S batteries connected in series to give us a nominal 400 volt system. I previously said that we would have 13 batteries in the main box and 5 in the secondary box. However, we only have room to fit 12 comfortably in the main box, so we will have 6 in the secondary box. The main battery box will sit down within the height of the main chassis frame rails, with the bottom of the box aligning with the bottom of the rails. This will provide for roughly half of the height of the batteries, with the upper half above the chassis rails sitting below the tunnel deck. Due to this configuration, we will be using a clamshell design for the box, using a lower tub with flanges that sit on the top of the chassis rails and an upper tub with flanges that sit on top of the lower tub flanges. The ends of the box will be full height, welded to the lower portion, and married up to the upper portion after the battery installation is complete. The batteries require several connections between each other and other equipment. As mentioned previously, my battery boxes are very snug, having to fit between the chassis rails, so this will influence how we handle these connections. The 3 types of connections are the high voltage connections, which will be handled primarily with copper bus bars, as well as shielded cable where connecting between the 2 boxes. Low voltage connections, which run between the battery circuit boards and the BMS to monitor battery status and health. And coolant lines, both supply and return, which run to the radiator and coolant pump to keep the batteries cool while discharging when the motors are running or while charging. I would also like to add a heat pump in the future that would allow me to heat the batteries during cold conditions and also provide heat for the cabin. We will get into each of these further after we look at the box construction. For the box construction, I am using 1/8 inch aluminum for the box components. As with previous steel parts, I designed these parts in Fusion and had them laser cut and bent by Oshcut. I needed to keep this somewhat thin due to the space constraints, so in order to reinforce this for the considerable weight of the batteries, I am installing trusses between the batteries in order to give the bottom tub adequate strength and stiffness. I will start the battery box construction by welding in these trusses. You'll notice at the coolant line end of the battery box, the trusses have a circular notch, which provides space for the lower of the 2 coolant lines. This gives us some space to get the upper coolant manifold in after the lower manifold is installed, and is necessary due to our tight space constraints. With the trusses welded in, we will continue by welding the end components. The ends are handled by several components that provide bump outs at the 4 corners. The bump outs allow us to stay compact in the middle where we want clearance at the motors, but gives us additional space where we need it at the corners for the various lines to exit the box, as well as room for their associated connections to be made, whether high voltage, low voltage, or coolant. With the main panels installed, we will install the flange at the top. The flange provides a mating surface for the top where we will apply sealant to provide a watertight seal. The mating surface for the top as it moves down at the end conditions is handled via the bends at the end components. Before welding these components into place, we drilled holes for the glands for our high voltage, low voltage, and coolant lines to exit the box at the front. The glands themselves will be installed later. Now we can move to the top. After checking for fit over the bottom, we will start by removing the openings at the access ports, which were only laser cut at 3 sides in order to keep our bends from warping. These ports allow us to get to the various main connections in the rare event that it is needed after the top is installed. The top does not have end conditions as the lower box ends go the full height, but we do need to install a little doghouse, which is there to provide room for and access to the high voltage connection on this end. As with the bottom, we have drilled a hole for the cable gland that is needed for the high voltage line. We have also drilled a hole in one of the access covers for a breather valve that will allow the pressure in the sealed box to stay constant as the batteries get warmer or cooler. At this point, we can temporarily place the top so that we can drill and tap holes that will secure the top, as well as secure the overall box to the chassis rails. We will also drill and tap holes for the access port cover fasteners. The top can now be removed and set aside for now. Next, we will apply several coats of liquid rubber along the side of the box that has the high voltage connections at both the lower and upper tub. Although the high voltage bus bars at this side will also be coated with rubber insulation, this provides an additional level of protection. After applying 2 coats of the liquid rubber, I placed the 3rd coat along with this poly fleece that helps to thicken the coating. We have also applied the liquid rubber at the joints in the box in order to provide water tightness. The joints will also eventually receive RTV sealant at the joints at the outside of the box. Moving back to the bottom tub, we need to install a board at the bottom of each battery bay in order to create space for the fins at the bottom of the batteries. I am using a corrugated plastic sheet which is relatively light but also strong enough to accept the weight of the batteries. After cutting the overall board to length and then ripping the individual boards to width, I am chamfering the bottom edges in order to allow clearance at the welds and then ripping a slot at the bottom of these boards to allow the battery fins to sit in. The last thing for the box construction is to install the various cable glands that keep the box watertight where we have our various line penetrations. For the high voltage wires and the coolant lines, these glands will cinch down tightly directly on the line. However, for the low voltage lines, since there are a number of small wires, we will use a flexible conduit for the wires to run through. The conduit will be installed once the secondary box is constructed. Here you can see the high voltage line gland and the low voltage conduit connection. And here you can see the 2 glands for the coolant lines. You can see here why we located the motor mount in this area lower on the chassis rail so as not to conflict with the coolant line exiting the battery box. With the box construction complete, we can talk a bit more about the high voltage connections for the battery modules. Stock bus bars that connect the Tesla Model S batteries are commercially available. However, I opted to have custom bus bars made so that I could control the exact spacing of the batteries and also to work around my trusses, which would conflict with the stock bus bars. I also gave them slotted holes so that I can ensure a tight fit to the face of the batteries to help with my space constraint issues. I had these bus bars fabricated by a company called Send Cut Send, which was a little cheaper than Oshcut for these copper parts, and the parts delivered by them are great. With the bus bars delivered, we need to provide an insulation coating on them, and I am applying several coats of liquid rubber as with the sides of the battery box. The low voltage connections that connect to the battery circuit boards require a little more discussion. First, I connected with a company called Vero Electric, which makes a BMS that works directly with the Tesla Model S battery boards. The stock Tesla batteries have circuit boards that are proprietary to Tesla's BMS system, so the typical route is to remove these boards and replace them with generic boards that can communicate with the generic BMS. But the Vero BMS has been developed to work with the Tesla battery boards and is a much simpler solution, since I do not have to replace the battery boards, but also the wiring is much simpler versus the custom low voltage wiring required between the generic boards and generic BMS. Vero sells plug-and-play wiring harnesses that daisy chain between the batteries, rather than the generic setup which requires running from each battery board back to the BMS. Unfortunately, the harnesses that Vero sells are a little too short for me since I need to route these harnesses up and around the top of the box, again due to my tight space constraints. So I am cutting these harnesses and splicing in extensions to give me the length that I need. Since these daisy chain from battery to battery, this is still much simpler than using generic boards and a generic BMS. Note that the Vero BMS does not make use of all of the pins on the Tesla board. This is due to the fact that the Tesla setup has some redundancy as a backup, which the Vero system does not use. Okay, so with the box construction complete and the high voltage bus bars and low voltage harnesses ready to go, we can now install the batteries into the box. Before installing, I am cleaning the battery terminals to remove the gunk around the original Tesla installation. I also double-checked the voltage on each module to ensure that they were balanced, and all modules were within a few hundredths of a volt, around 21.3 volts each. Because of my tight space constraints, the installation of the batteries is a little tricky. First, I need to plug in the low voltage board harnesses ahead of the battery installation, since this needs to feed down in between the trusses where I can't access after the module is placed in the box. I am also taping the wires tight to the module where they feed down into the truss area. The first module has a bus bar that brings the bottom connection point up to the top where it is accessible to make the connection, and I have pre-installed that onto the module ahead of placing it. After the module is placed, I am sliding in a piece of 1/8 inch thick rubber between the box and the bus bar just to provide an additional layer of protection. Once the rubber is placed, I am sliding the battery tight to the high voltage side in order to leave as much room as possible on the cooling side. We'll need it due to our tight space constraints. The first module has additional space between the front face of the module and the front of the box due to the room needed to clear the mating flange at the top. In order to fill this space to prevent the module from moving, I'm inserting a piece of 3/8 inch thick neoprene foam sheet along with a 1/8 inch thick sheet of ABS plastic. On the opposite side of the module, I am placing the 1/8 inch ABS plastic sheet only to fill the space between the module and truss for a tight fit. Note that the bus bar has a top and bottom. The top has the longer leg and the bottom has the shorter leg. This is necessary in order to keep the bus bars a healthy distance away from the trusses. For each subsequent module, I am loosely installing the next bus bar onto the module that is installed. Now we will place the orange insulating cap over the bottom connection of the module. I haven't done it yet, but I'll slide that sheet of ABS plastic partially over the cap to help prevent it from popping off. Once we get to this second module, we need to use electrically insulated gloves with leather gloves over the top, since our voltage will now be adding up to a potentially deadly level. As before, we will place the rubber sheet between the box wall and the bus bar and then shift the box tight to the high voltage side. Next, we will install the bolt for the bottom connection of the second module. I am using an insulated ratchet and socket to tighten this bolt. With the bottom bolt tightened, we can now tighten the top bolt using an insulated wrench. The rest of the modules are repetitive until we get to the end. Note that for the cap at the top, I am inserting a piece of folded neoprene sheet in order to keep this cap from popping off. The last module has a slightly different low voltage battery board connector. Instead of having two pairs of 3 wires coming from the circuit board, this one has one 3-wire whip that connects to the previous battery and one 1-wire whip with a long extension that runs up to the front of the box. This 1 wire will connect to one of the 4 connections going to the BMS, with the other 3 wires from the BMS going to the first battery in our secondary box. This last module also has a different bus bar at the top that will accept the high voltage line coming into the box. With the modules in place, we can now connect the low voltage circuit board harnesses together. And we will now place 3/8 neoprene sheet at the upper portion between modules in order to snug them up and prevent them from moving around in the box. With the batteries installed, we can now handle the final step, which is installing the cooling manifolds. For the coolant lines, I am using the stock connectors of the batteries, which I actually got for free with the batteries. I just need to remove the stock plastic tubing, which I am replacing with rubber tubing, so that I can control the length and the downstream connections at the manifold. The rubber tubing from the battery connectors has a 5/16 inch inner diameter, and these connect to T's that also have a 5/16 inch leg for the battery connections and 2 1/2 inch legs for the manifolds for 1/2 inch inner diameter manifold hoses. Both the 5/16 inch hose and the 1/2 inch hose are connected to the T's and to the battery connectors with Oetiker clamps, which are permanent and very solid. Because of my tight space constraints, I need to prefabricate the manifolds and then drop into the box and click the connections into place, and this was really tricky and time consuming to get each connector lined up and clicked into place. You can see where I am leaving a longer length coming out of the front of the box, which will go to the secondary box. The upper manifold is constructed the same as the lower manifold, but is much easier to install since I have full access at the top. Finally, I am testing the cooling lines to ensure that we have no leaks. I am testing this at just over 2 psi using a Schrader valve with a bicycle pump to pump in air at one of the lines and a gauge at the other line. I left this gauge on overnight and it held. Okay, so that's it for now. We will keep the box top off until we get further along and can fully test all the systems. Next time we will build the front battery control box and install the remaining batteries. See you next time.